Hello everyone. Now that we've gone over a definition of a manifold mesh and an oriented manifold mesh, I'd like to talk about data structures for actually storing meshes in memory so that we can deal with them in code. And I'll restrict myself to triangle meshes to begin with because the analysis will be a little bit simpler, but I will point out where we can generalize our data structures to manifold meshes with arbitrary polygons. Okay, but first I want to get a handle on just how much data I need to store. So let me try to figure out how many edges there are and how many faces there are given a certain number of vertices on the mesh. So to do that, I have to turn back to my Euler characteristic chi, which, if you remember, that is equal to the number of vertices minus the number of edges plus the number of faces. If we're in a watertight mesh, we have an interpretation of chi as 2 minus 2 times the genus, where the genus is the number of handles or piercings that you have in the watertight mesh. So, for example, for Homer, he doesn't have any handles that I can grab and form a loop through. So we would say he has a genus of 0. Or another way to look at that is I can blow Homer up to a sphere, which doesn't have any handles. So that means that the Euler characteristic of Homer should be 2 minus 2 times 0, which is 2. And if we check that, we look at the number of vertices minus the number of edges plus the number of faces, and we get 2. So that's kind of interesting. If, by contrast, I pick a mesh with a handle like the teapot, this does have a genus that's not 0. It has one handle, one thing I can grab onto and form a loop with my hand. And so we would say that has an Euler characteristic of 2 minus 2 times 1, which is 0. And so that means the number of faces minus the number of edges, plus the number of vertices minus the number of edges, plus the number of faces is equal to 0. Okay. Now, one thing I didn't cover is how do you deal with non-watertight meshes? So in all these cases, these meshes do not have a boundary. So remember, the definition of a boundary is a sequence of connected edges that all have exactly one face. So if I open up this dynopet that we've been looking at, and I look at the edges here, I see there are a few places. In fact, every fingertip and every toe tip has a boundary cycle. So every boundary is a cycle. That was part of what I introduced when I introduced the manifold meshes. And a boundary component is a sequence of connected edges that forms a cycle where every single edge has exactly one face on one side. So in a manifold mesh, we can have at most 2 faces incident on each edge, attached to each edge. But the boundary has exactly one on all the edges that are on it. And the interesting thing about the boundaries, they'll always be cycles like this. All right? So this relationship I gave you for the Euler characteristic only applies for watertight meshes, so meshes that don't have any cycle boundaries like this. They don't have any chunks taken out of them, where I can get from the outside to the inside. Like the teapot, I could not, even though it had a handle, that's a little bit different, I could not get from the outside to the inside of it. This particular teapot, the spout was plugged up. So actually it can hold water. There's nowhere I can pour water out of it. Okay, so this is a watertight teapot. Maybe a bit of an unusual teapot, but it only has one handle. Okay, no boundaries. Whereas the dynopet has boundaries. In fact, dynopet has 10 boundaries because it's got 3 on each finger, so 6 of those, and 2 on each toe. So it's got 10 boundaries. So in order to get a relationship for the Euler characteristic for meshes with boundary, we have to consider what would the genus be if we plugged up the boundary. Now, every time I plug up a boundary, it's equivalent to adding one face, topologically equivalent. This is sort of the argument that I used when we were talking about the connected sums. That's how I proved what the connected sum would do. So I know these boundary cycles certainly have more than one triangle that have been taken out of them, but I'm telling you it's actually topologically equivalent to taking out one face. Really, that's the way you can think about it. It's topologically equivalent to taking out one face. And so every time I take a boundary cycle out, the number of faces goes down by 1. Every time I plug it up, the number of faces goes up by 1. So it's like I didn't have to add any new edges or vertices, topologically equivalent to adding 1 face. Okay, so if I plug this dyno up, I add 10 faces, and then the genus is 0 because he doesn't actually have any handles. So genus 0, we know the Euler characteristic is 2. But now if I punch these holes out again, I have to subtract 10 faces. So if you put that all together, what we could say is, okay, for a water-type mesh, the Euler characteristic is 2 minus 2 times the genus. We would say for a non-water-type mesh, it would be 2 minus 2 times, I'll say G prime, that's like the genus you get. So I'll say G prime is genus from plugging up all boundary cycles. So it's 2 minus 2G prime minus the number of boundary cycles. All right, so here the genus, if I plug these up again, would be 0. So 2 minus 0 minus 10. So this Euler characteristic should actually be negative 8. So if we look at that, I got 2039 minus 6046 plus 3999, and indeed, I get negative 8. So that's like kind of magical. Pretty cool, right? So this is why one of the reasons the Euler characteristic is such a cool topological invariant, because you don't need to know how this thing is actually meshed. You don't need to know how many triangles or vertices. You just look at these coarser topological properties, genus and boundary cycles, and you can actually say what this number will be. All right. But why did I said I was going to be talking about data structures. Why did I just talk about all this? Well, if I assume that G and the number of boundary cycles are both much less than the number of vertices, then I can assume that Euler characteristic is about 0. So I can assume that x is about equal to 0, which implies that v minus e plus f is 0. Right? So that's just going to, v minus e plus f is approximately equal to 0. I mean, this is certainly true about all the meshes I've been looking at, right? So there's only 10 boundary cycles here. That is significantly smaller than the number of vertices. 0 handle is certainly smaller than the number of vertices. So when I'm trying to, assess the relationship between vertices, edges, and faces, helpful for me to make that assumption. Okay, one more thing I need to look at here, and then I'll be able to piece everything together, is how many edges are there for a particular number of faces. And so for this, let me remember that I'm dealing with triangle meshes here. So each face is going to have 3 edges on it. And the other thing that I'll remember here is that, okay, just trying to get this right here. Okay, so each face has 3 edges. So if I count the number of faces, it might seem like I have 3 times as many edges as that, right? But we also remember we're in a mostly water-type mesh, right? There might be some boundary cycles, but we're going to assume that most of the edges actually have 2 faces incident on them. And so what that means is, hey, it looks like each face counts 3 edges, but each edge gets double counted if we have the faces counting the edges. So what I would say actually is that, okay, it seems like I've got 3 times, so I would say, it seems like I got 3 times as many edges as faces, but actually they're double counted. So we would say, on a water-type mesh, actually, this is exactly true. On a non-water-type mesh, if there aren't too many boundary cycles, this is approximately true. So we have that. And actually, just to check that, if I look at, let's say I go back to Homer. So I'm saying, okay, the number of edges should be 1.5 times the number of faces. So let me just see that. If I multiply this number by 1.5, I get exactly 73032. So I'm not lying to you, or at least proof by example. That's not what we want to do, but it works there on that example. Okay. So that's what we can say. And actually, what we can do now is plug this into the Euler characteristic. If I assume the Euler characteristic is approximately 0, low genus, few number of boundary cycles, then I'll substitute this in. I'll say, okay, v minus e, which I'm now going to say is 3f over 2, plus f is approximately equal to 0. And so that simplifies to v minus 1/2 equal to, or v minus f over 2 is approximately equal to 0. So therefore, v is approximately equal, or sorry, f is approximately equal to 2v. All right, so there are approximately twice as many faces as vertices. I can look at that and I can see that's true. And then, well, because of this relationship I just established, then it follows very quickly that the number of edges is approximately 3 times the number of vertices. Okay, so that's the data we're working with. Okay, I'm trying to get this all in a good place here. All right, so let's say I had this triangle mesh here. It's got 5 vertices. I'm labeling them 0, 1, 2, 3, 4, and I'm depicting what the 3D coordinates of them would be. And then I've got 3 triangles, 0, 1, and 2. So how would I store that information in memory so that I could reconstruct this? So let me start with what I'll call here the naive data structure. So this is called the naive data structure. And what I'm going to do is just say, okay, for every triangle, let me just collect all of the coordinates of the vertices that are involved. So to draw this first triangle, I'm going to need x0, y0, z0, and then x3, y3, z3, and then x4, y4, z4. And then I'll keep doing this for the rest of them. Okay, so here's how it all shakes out. And if I look at this, what I can say is, okay, each face has 9 pieces of information associated to it. So it's got, 3 coordinates x, y, z for each of the 3 vertices. So I would say this takes up 9 times f memory. But actually, this is approximately equal to actually 18 v memory. Because I remember that the number of faces is approximately equal to 2 times the number of vertices. And so that's how much memory this takes up. So that seems like maybe a lot of memory. 18 times the number of vertices. And the other downside of this is if I change one of the vertices, let's say this one, right? So x3, y3, z3. We'll actually have to go through every single triangle and update that particular vertex. So I'd have to update it here in this one. I'd have to update it here in this one. I have to update it here in this one. So you actually have to go through and find every single triangle that this belongs to and update it. And so that's a little bit tedious. So it turns out there's a much better data structure you can use, and I'll call index storage. And this is actually the format that the .off files use. And these are the files that we've been using in the library ggslack. These are the files that we've been using when we've looked at meshes in our scenes. So this is the data structure that they use. And it's also the data structure that our graphics cards use when they render the meshes, when they draw them to the screen. And so what we're going to do is, instead of storing like this one table with all the vertex information for each triangle, we're actually going to decouple the geometry from the topology. We're actually going to use 2 tables here. And so what I'm going to do is I'm going to make the first table with just the coordinates of the vertices that are involved. So I'm not going to worry at all about the triangles or the connectivity information. I'm just going to put in the location, the x coordinate, the y coordinate, and the z coordinate of each vertex. Okay, so let me just do that real quick. Okay, so there it is. And now what I'm going to do is I'm actually going to create a second table whose sole purpose is to store the faces. And so we would say that's the connectivity or the topological information. And I'm going to completely separate that from the geometric or the vertex information. And so what I'll do is I'll have each row of this table index the rows of this table. So you want to know how to draw the first face? Well, I'm going to tell you the first face, face 0, is made up of vertices 0, 3, and 4. And so rather than storing coordinates explicitly, I'm basically storing pointers. I'm going to say, okay, look up row 0, row 3, and row 4 in the vertex table. Now you have the coordinates that you need to draw the first face. To to draw the second face, that's going to be coordinates, that's going to be vertices 0, 1, and 3. And to draw the third face, okay, so I got 0, 1, 3. To draw the third face, it's going to be 1, 2, 3. So there's all my topological information. And what's very neat about this is now I can make a change to one of the rows in the vertices, and that change will automatically update all the faces. I do not have to change anything in the face table. And this is a really good data structure if you want to be changing the vertices continuously, but you don't need to change the faces. So a great example of this would be if I go to our graphics website and I go to our assignment 3, and you look at this Homer mesh that I was animating after I skinned it and rigged it. I don't need to change any of the triangles to make Homer move. I just need to update the position of the vertices. So that's one of the advantages of decoupling the geometry from the topology. Okay, so geometry is a completely separate thing. The locations of vertices is a completely separate thing from how they're connected to each other. The other advantage is it's actually just more efficient, right? So what I have here is, okay, this vertex table stores 3V pieces of information, and the faces table stores 3F pieces of information. So this is 3V pieces of information. This over here is 3F pieces of information. Altogether, 3V plus 3F is actually 9V, right? Because we know there's twice as many faces as our vertices. So I would say 3V plus 3F, which is approximately equal to 3V plus 2 times 3F, which is equal to 9V. So actually the memory is also better than the memory was for this naive structure. And so this is a very commonly used data structure. It's used in all the meshes in the library ggslack that I gave you. So for example, if I wanted to look at Homer, if I open up Homer, I can show you the OFF file format, the .off file format. First, it tells you how many vertices there are and how many faces there are. And then it gives you the vertex table first. So there's going to be 24,346 lines of XYZ, XYZ, XYZ. And then if we scroll down far enough, we'll eventually get to the next table, which is the index storage for the faces. And here it is. There is one extra thing here. The OFF file format can actually accommodate non-triangular faces, so it actually has an extra field at the beginning which says how many vertices make up each face. So as an example of a mesh with non-triangular faces, if I open up this dodecahedron here, this has pentagonal faces. If I were to look at that file, dodecahedron, it's got 12 pentagonal faces, 20 vertices. So if I open that up, I will see, here we go, 20 vertices, 12 faces. So we got the 20 vertices there. And then notice that the faces say that they actually have 5 vertices. All right, so that's the OFF file format. And again, this is what's used to render. So when you want to go render something, you copy over 2 buffers. One of them is the vertex buffer. So we'll talk about this more later, but one of them is the vertex buffer. The other one is the index buffer. And that's, on the graphics card, it actually is all triangles. So you pass these along. 2 different buffers. Okay. But just to show you, there are some other even more specialized data structures if your mesh has a special structure that you can use. So one of them is called a triangle fan. And if I look at this, the way it works is, so let me draw an example here. This is a mesh with a very particular kind of topology. So this is a mesh where you have this central vertex. So I'll call this vertex 0. And then you have a list of other vertices that each come off of this. So there's 0, I'll put 1 here. This is 2. Give me a second, I'll fill the rest of these in. Actually, I decided to go the other way, so these are counterclockwise, just so I keep with that convention. But anyway, so what you do is, okay, vertex 0 is considered the central vertex here. And what I do is I just keep making triangles with respect to that vertex. So I'll make a triangle with a base 1, 2. Then I'll make a triangle with a base 2, 3, and 0 at the tip. I'll make a triangle with a base 4, 3, and 0 at the tip. I'll make a triangle with base 5, 4, and 0 at the tip. And finally make a triangle with a base 6, 5, and 0 as the tip in this example. So this is a very special structure. Most meshes are not like this. This one is a triangle fan. But certainly Homer's not a triangle fan. I can find, as soon as I like do something like this, where I'll create, a triangle that doesn't have 0 as the central vertex. So if I change the mesh to include this triangle as well, that's no longer a triangle fan. Okay, so they all have to be coming off of a central vertex. And in that case, I actually, if that's what I do, and I lay out the vertices in this very particular order, so they have to go in this order, one to the next to the next. I can't jump around. But if they actually go sequentially in this way, and I specify them in that order, well, I actually only need to store the vertex positions. So that means that I actually only need 3V memory, right? So it's like I could just get away with this table here of the vertex geometry, but I just need to make sure that it actually is a triangle fan, and that they're specified in this very special order. All right? So that's called a triangle fan. There's actually another kind of topological pattern that's amenable to a compressed format like this, which is called a triangle strip. So in addition to a triangle fan, there is another kind of structure you can make here, where I guess I'll start over here, or let's see, what should I do? No, I'll start over here. So okay, this is vertex 0. And so what you do is actually you think about alternating these up and down now. So I'll say, okay, this here is vertex 0. This is vertex 1. This is vertex 2. Now they don't have to be perfectly up and down. Maybe I'll move them around a little bit. Maybe I'll put this like more like that, and maybe this is more like over here. So 0, 1, 2, 3. But the point is somehow there's like a top of this strip and a bottom of the strip. And if I'm very careful about the order that I put these in. So somehow I have all the odd indices at the top and all the even indices at the bottom. If that's the convention that I follow, then I can assume that the connections are like this. So I'm going to make a triangle from 0, 1 to 2. So let me do that real quick. Oops, I'm trying to make the triangle here. So I make a triangle from 0, 1 to 2. And then now I'm going to make a triangle from 1, 2 to 3. And now I'm going to make a triangle from 2, 3 to 4. And so it goes 0, 1, 2, 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6. So you just keep sliding along by 1. So there we have 4, 5, 6, 5, 6, 7. And that's your triangle strip. So notice this didn't have to be like a triangle fan. We didn't have to have that one central vertex, but it does have a strip structure. So it has a top and a bottom. And this also has 3V memory, right? If I lay out the vertices in this special order, then the triangles are implied. And so when memory used to be more precious than it is now, some of the early techniques for doing lossless compression of meshes would try to find regions of the mesh that look like triangle fans and regions of the mesh that look like triangle strips and encode them separately. So if I went back to Homer and I had a look at this, I can certainly find some triangle fans here, right? Like there's a triangle fan, I can see it. So I would somehow like cleverly decompose this into triangle fans and triangle strips. Actually, here's a nice triangle strip I see, kind of starts over there, goes boom, 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 right? That's a nice long triangle strip. So anyway, that's kind of a cool way to compress meshes. So this is a great starting point. And so what I'll do is I'll just ask a quick question about triangle fans or triangle strips. But then I'll show you some of the limitations of this. We'll focus more on the general one here. Show you some limitations of this, even though this is still pretty compact in memory. Okay.